So, welcome student. In today's class we are going to discuss the ILP formulation of the scheduling problem. So, in the previous class we have seen that this scheduling is a step where we are actually decide the time step of each operations. That means, if there are set of operations, we decide in which time step which operation is going to be executed, right. And also we have seen in the previous two classes that once we are given a program which is consist of a loops and if else branch everything, what we do, we identify the CDFG control and data flow graph of that, and then we take the each basic block at a time. So, one of the block at a time and try to schedule the operations, right. This is how we have discussed so far, and then for that particular basic block we can schedule the operations, and then we can combine the schedule of all basic blocks, and then we can actually have a schedule of the complete operations, right. So, for example, this is the example I have taken in the last class, that if you have a while loop like this. So, we have extract the CDFG where this is a basic block, this is the basic block within the while loop, and this is the basic block at the end, and this basic block represent this code, right. And in throughout this class we try to take this particular behavior and we will discuss all these algorithms for scheduling and then allocation and binding with respect to this example, right. So, and then this is what is the plan. So, we have seen that for now, if you consider this particular basic block, that whatever the operations are here, they are actually written in the 3 address form, right. So, that means we split the operation into smaller unit or level operations, because otherwise the delay to execute a single operations will be more, right. So, that is why that is not feasible. So, we do that, and then what we did is that from this we identify the data dependency, right. So, this is what is called DAG. It is basically direct acyclic graph where we actually represent the data dependency. And what is the data dependency? If some variable is getting defined somewhere and it is used in some different other variable, there is a dependency. For example, here T1 is defined in V1 and that is getting used in defining T5. So, there is a dependency. So, this is my T1 operation which is doing this U plus dx, and that particular things is going to T5, right. So, where this T5 is getting calculated, right. So, this is what is the data dependency graph which we extract from the operations of a basic block, right. And then what we have seen that, and this graph is something is a DAG, which is direct acyclic graph. There is no cycle, because it is a for flow of data kind of top to bottom, right, because the operations are sequential in C code. So, there is no kind of cyclic dependency within a basic block, because there is no loop, nothing, right. So, this is something I have given. So, we have this data dependency graph, and then what we convert this into a sequence graph where we just say key, instead of keeping all these variable names and all, because they are not so important during scheduling, what we do is just merge all this input to a single node which is called source, and all the output into a single node which is called sink, right. So, this is the model of a basic block, right. So, it is representing the informations of the basic block, the data dependency among the basic block, right. And right. So, now what is scheduling? Given such sequence graph, it determines in which time stamp which operation to be executed, right. So, here is an example. So, basically you decide that this operation is going to be executed in time step 1, this operation is going to execute in time step 2, this operation is going to be executed in time step 3, and this is in time step 4, and so on. So, this is the job of the scheduling. Okay. So, if I just recap what we have defined the formally the scheduling problem, that you have given the sequence graph, that means the operations and their dependencies within a basic block, and also we have discussed that this each operation is not always single cycle, right. The operation might take multiple clock to execute in hardware, right. So, there is a delay associated with each node. If there are n nodes, each node had a delay di, right. Node Vi has a delay di, that means this particular operation will take d cycle of clock in hardware execution. Okay. And optionally we usually given the resource or timing constraint, that it is not something in hardware, it is unlimited resource. So, you might have a limited number of resource, you try to schedule the operations using the resource available to you, or sometime you might given this timing constant or the latency constant, that this is the time step is given to you, schedule the operation using minimum number of resource, right. And then given this input, your scheduling does is it identify the start time of each operation Ti, right. So, Vi starts at time step Ti. So, when the operation starts, and also inherently it give the total latency, that is the total number of cycle needed to execute the entire behavior, right. So, that is something is a scheduling problem, and you have to make sure that whenever you assign timestamp, the data dependency is not violated, right. So, the data dependency in the sense that if there is a node Vi to Vj and there is a data dependency, this must be scheduled and complete its execution, then only I can start this operation, right. So, if this is a 2 cycle operations, if its timestamp say starting at 3, so only I can start this operation at timestamp 5 or more, right. I cannot start this anything beyond 5, right. So, that is what is the dependencies. Okay. So, this is what we have already discussed in the previous classes, and then based on this constraint or the given, you can have 3 kind of scheduling problem. One is first is the unconstraint, where there is no resource or timing constant, you just schedule and then you try to identify the minimum number of timestamp, because since there is no resource constraint, your objective is try to schedule the all operations as low as using minimum number timestamp, right. But the 2 practical algorithms that is of our interest is the MLRC and MRLC, right. So, minimum latency or minimize latency under resource constraint or minimize resource under latency constraint. So, here the resource constraint is given. So, I have given this much resource is available, you schedule the operations, but you try to minimize the number of timestamp needed to execute the behavior, and this is the dual problem. I have given a latency constant, I have said that you schedule in say 5 timestamp, but you use the minimum, you try to minimize the resource usage, right. These are the 2 dual problem, it is just a opposite problem the others, and these are the 2 problems which is actually practically important, because most of the time we are bounded by the resource constant or timing constant. So, we have to come up with some schedule which actually satisfy this given constant, right. So, and also we have seen that this scheduling problem for general DAG is a NP complete problem. So, what does it mean, the NP complete? So, NP complete is the problem for which you cannot have an algorithm which can polynomial time, it is a deterministic polynomial time algorithm does not exist which can give a optimal solution. Okay. So, that means we need a exponential algorithm to get the best solution. So, for example, I have given a DAG or the dependency graph, and I say you have this say this much of resource, you identify the minimum number of timestamp needed for this using this resource. So, for generic DAG, this problem is NP complete. I mean, what is the intuition? I am not going to prove why this is NP complete, but the intuition here is, since there is a dependency of the operations is given, so you cannot just statically determine that if I schedule these operations here, that guaranteed the rest of the operation will be scheduled using the given timestamp, right. Or if it does not guarantee that if you just try to schedule this first timestamp, you cannot determine which are the operation to be scheduled here, so that I can actually schedule the other operation using the minimum number of timestamp. Okay. So, so basically in the other sense, since the operation can be scheduled in timestamp, there are many possibilities of scheduling. Ideally, the exponential algorithm means what is it actually check all possible such mapping or scheduling and give you the best one, right. So, without exploring all such possibilities, having the best solution, identifying the best solution is not possible for NP complete problem. Okay. So, let us not go into the detail of such proofs and all, but the basic bottom line of this scheduling problem is computationally hard problem, right. In the sense, you cannot have a polynomial time algorithm like if the number of nodes in the graph is n, say order of n or order of n square or order of n q. So, this kind of algorithm does not exist, or you cannot have an algorithm of this which can give you the best solution. Okay. So, to get the best solution, you have to go for exponential algorithm. Okay. So, that is why this is a hard problem, And there are two approach to solve this problem. The first one is the obviously if you want to get the exact or the optimal solution, you have to go by ILP formulation. Okay, we will talk about that in today's class, that integer linear programming model, which can give you the optimal solution, guaranteed to give you the optimal solution. But in most of the cases in practice, because this is a computationally hard problem, we usually apply the heuristic algorithm, right. So, we actually have some kind of with some efficient algorithm like order of n or say n log n, this kind of algorithm, which give you the good solution. It may not be the best always, but the solution is good enough for the most of the scenarios. Okay. And since this timing the running this EDA tools are basically of our prime importance, most of the time we usually go for this heuristic based solution to solve the scheduling problem. So, we are going to discuss about all such problems in this particular course. In today we try to see how we can model this scheduling problem using ILP, okay, integer linear programming. So, just to go into that formulating the problem, let us try to understand what is this integer linear programming first of all, right. So, first let us try to understand from the higher level that, so what is the objective here. So, in this ILP problem, so if you have a optimization problem, either say minimize something or maximize something, you try to solve that. So, what is the thing? So, you have some minimization objective, right. So, you have a minimization objective, say suppose you have a minimization objective, say x1 plus 2x2 should be minimum, right. So, you have two unknown variable x1 and x2, and you want to find out the value of this x1 and x2 such that the expression x1 plus 2x2 is minimum. Okay. So, this is your optimization objective. Okay. So, that means whenever you try to solve try to model this problem as ILP, you have set of unknown variables, right. So, suppose you have, in general you might have say n unknown variables, okay, say x1 to xn. Okay. So, this is something unknown variable and we want to identify the value of these variables, and with an objective to minimize or maximize certain expression, okay, or some optimization function. Okay. So, is it something the end of it? No, basically now these variables can be integer, right. So, then since integer linear programming, we will assume this variables is actually integer. So, integer can have a range. So, but this x and x2 may not take all possible values, right. So, there will be some constraint on these variables. Okay. So, that constraint is given by a matrix which is called m into n. So, there are m such constraint. For example, say suppose you have two variables x1 x2 and you are saying x1 minus x2 should be greater than or equal to 0, and say you are saying 3x1 plus 5x2 should be greater than or equal to 5, and so on. Say I am just arbitrarily giving things. So, there are two constraints, right. So, so how this matrix will be represented? So, this is 1 into this, 1 into this. So, it is 1 and minus 1, 3 and 5, right. So, this matrix A is this, right. So, which is something we can always represent this by and matrix by the coefficient of those expressions, right. And so, this is basically how many column will be there. It is basically the number of variables. So, this is n, and if there are m constant, it is m into n matrix. Okay. And we also have this constant. So, the right hand side, which is basically my this b, right. So, it is basically it the represented as like a into x. X is that list of variables to us should be less than or equal to b. Okay. So, basically it is nothing but we have set up expressions, and those expressions define certain constant on the variables, and those constant expression you can in high level you can assume this way, and we can represent this expression by a this kind of matrix operations, because if I just multiply this constant with this matrix with x, x is basically 1 into n, right. So, if I just assume that this is basically n into 1, right, this is the say 1, the variable is x1 to xn. So, it is n into 1. So, we will get this m into 1 expressions, right. So, that something is there. So, the bottom line is that there are set of unknown variables, I have a optimization objective and I have given set of constraint, and this constraint you have to understand what is a linear means. It is basically this expression should be linear, right. So, there is no non-linear term. So, non-linear means what? You do not have a term like x1 square or x1 into x2 into x3. See here it is every variable is multiplied by constant. There is no multiplication of two variables, right. So, then that will be non-linear expressions. So, this constant must be linear, right. So, that is the that is why it is a linear integer linear programming, and these unknown variables are integer, right. And then what this ILP does, given such set of constraint and a objective function, it try to give you, it will give you the value of this variable x1, x2 and all those unknown variable xn, such that the value of this optimization objective is minimum, right. Whatever the it satisfy the minimum optimization objective, right. So, that is what is the ILP solved. So, again we do not want to go into detail how this ILP works and all, because that is something is not the objective of this course, but what we try to do in this course is something, how can I model this scheduling as this problem, because you understand the scheduling is also an optimization problem. Either you try to optimize this resource under latency constraint, or you try to optimize the latency under resource constraint. So, there is an optimization objective, and you try to schedule the operations. So, that means your operations are the schedule time is the variable for us. I do not know which timestamp which operation to be executed in which timestamp, right. So, that means that a timestamp where a variable going to be executed is kind of a unknown things to us, and that was the variable to us, and I try to schedule the operation, try to find out the value of those variables such that this my optimization objective, either it is a latency or resource, is satisfied, right. That is what is our modeling of this scheduling problem as ILP. Okay. We will go into detail in this today's class. So, just to give an example for this ILP, so this is linear programming. So, what is the difference between ILP and linear programming? If the variable is linear, that means it is a continuous, or you can think about a floating value, it can take any value, then it is linear programming. And if these variables are actually take only integer value or discrete value 1, 2, 3, 4 and so on, then it is a integer linear programming. Okay. So, here is a nice example. Say suppose my two variables are there, x1 and x2, and then my optimization function is this, right. So, this x1 minus x1 plus x2, okay. That I want to do a maximize, it can be minimize or maximize. So, here you see the minimization objective I have written as a CT is x, right. So, that means this C is a constant, right. The constant is something, so for this example, the example I have taken, it is the 1 and 2, right. This is my C. So, CT means C transpose, right. So, this is my the variable. So, here I can say that this is my C and this is my variable. So, this is basically, you can understand that 1 into n, this is the matrix, this one, and this one is basically n into 1. So, if I multiply, I will get this expression, nothing else, right. So, this is n into 1. So, that will give you my expressions, okay. And say suppose these are the constant given that this should satisfy. So, you can see here that if I apply this constant, so basically it restricts the, because this x1 and x2 can take any values, this x1, this constant actually restrict that it cannot take other values, right. For example, here if you say this is my x1 and this is my x2, so x1 can take any value in this range and x2 can take any value in this range, but this expression say that your value cannot go beyond this, x1 cannot go beyond 5 and x2 cannot go beyond some 2.5 or something, okay. And this expression says that your value of x1 x2 cannot go beyond this, and this basically restricts the other values because it can go this way also. So, this is my the possible value set, right. This is basically the solution space. So, this is my solution space, this yellow part is a solution space for this, and what is my, so there are many solutions here. I want to identify the value of x1 such that this particular function goes the maximum value, right. So, now if you try to solve this, so if you just put these values, right. So, if your x equal to 1 and y equal to sorry x1 x2 is this, or if your x1 is this value and x2 is this value which is say 1.2 or 1.3 and so on, in all cases you will get your f equal to 0. So, if so for this all this value in this line will give you the f equal to 0, right. Similarly, if you take the value in this range, your f equal to 1, but the maximum value will get. So, for these values of x y, x 1 and x 2, your maximum value is f value is 1.6, and which is the maximum value, and you can see here even for that there are many values possible for x 1 and x 2, and this is the value which you give you the. So, which is basically for this x 1 and x 2 you are getting for this particular value, right. So, your x 1 equal to 0.06 and x 2 equal to 2.2. Okay. So, the idea here is this is just an example that you try to find a value of this x 1 is x 2 such that you get the value of this your this objective function maximum. Okay. So, now move on to our problem. So, our problem is scheduling. In our scheduling, what I want to do is we want to schedule the operations, that means I want to assign the timestamp. Okay. So, for my problem, what is my variable? So, that first you have to identify, right. So, so what is not known to us? The operations, why did get time schedule, right. So, that is not known to me. So, that should be the variable, right. So, what we did, we for that we take a variable which is called xil. Okay. So, what is that? So, xil is basically 1 if the operation v1 starts at timestamp L. Okay. So, that means it is going to execute, it is assigned timestamp L, right, and since it is a multiple, it may be the delay d. So, it can start execution from L and it can go L1 L plus 1 L plus 2 to L plus d minus 1, because it is delay, it has some delay, right, but it starts its execution from timestamp L. So, that is something is not known to me. So, I am going to get a variable which is basically xil, which is something 1 if this operation vi start its execution from timestamp L, otherwise this value is 0. Okay. So, this is the variable, because in any ILP formulation I want to have some unknown variable, I want to find the values. So, if I identify the value of this xil for all possible xil, then I know what is the start time of each operation. Okay. So, let us try to understand how many such variables we need. So, suppose you have given a latency bound is L plus 1. So, limit is lambda, and so since it is a lambda, that means this sync node will be scheduled and lambda plus 1. So, we assume that the possible timestamp is basically lambda plus 1, and there are say n number of operations. Okay. So, how many such variables is possible in worst case is basically n into L, or say n into lambda plus 1, right, because any operations can schedule in any timestamp ideally. So, I need this many variables, right. So, for example, say for operation v1, how many variables are there? Say suppose my lambda equal to 4. Okay. So, how many variables are possible? So, x11, x12, x13 and x14. Okay. So, what does it mean? So, if the operations v1 is scheduled in timestamp 1, this then x11 is true. If the operation 1 is scheduled in timestamp 2, then this is 1, other variable will be 0. If the operation 1 or v1 scheduled in timestamp 3, then this will be 1 and rest of the variable will be 0. Similarly, if this variable operation v1 scheduled in timestamp 4, then this will be 1 and rest of the variable will be 0, right. So, that is why, because I do not know this where this operation v1 is going to schedule. So, it can schedule in any timestamp given. So, I will assume these many variables are there and total number of variable will be this. So, this is obviously the upper limit of variables, right, and if you understand in my previous modeling the expressions, right. So, constant it depends on the number of variable. So, if the number of variable is more, this expression or the constant expression will be more, and so I mean obviously if you understand, if the number of unknown variable is more, your solution or solving the problem is difficult, right. So, the question here is that obviously in this model that I can have n into lambda plus 1 number of unknown variables, can I reduce it, right? That is a question 2, and the concept here is that we can actually utilize the ASAP and ALAP solution that we have already discussed in the previous class to minimize this number of variable. Okay. So, let us try to give the intuition. So, for example, here say suppose you have 4 time step is given, right. So, suppose your lambda is given 4. So, lambda plus 1 is 5. So, if you already know this, in this case, since these operations after that there are 3 operations, right. So, this operation never can schedule in time stamp 4, then I cannot schedule everything in 4 time stamp, because if if schedule is time stamp 4, this will be scheduled in 5, this will be scheduled in 6, this should be scheduled in 7, which is not a valid solution, because you want to schedule everything within say time stamp 4. So, that means that although logically any operation can schedule in every time stamp, but because of the dependency it is not possible to schedule most of the time. A variable cannot be scheduled in any time stamp, rather in a span, okay. And that span can be identified by the ASAP and ILP. Okay, let me try to explain that. Say the ASAP is something as soon as possible, it is an unconstant schedule. So, it basically whenever the predecessors operations are already scheduled, the operations on which it depends are already scheduled, then what is going to, it is going to schedule the operations, right. So, if you take that particular graph and try to do a ASAP, you will get this solution, right. So, for example, here these 5 operations will be scheduled in time stamp 1, because it depends on the inputs, right, and I can assume that inputs are available, and I am assuming all the operations are here single cycle, but you can always model this as a multi cycle operation as well, okay. And once these operations are done, I am going to schedule the next set of operations in time stamp 2, right, and so on. This is already I have discussed in the previous class. So, this gives you the minimum value of lambda. So, this is because it is an unconstant schedule, you never thought about the resource. So, the ASAP always give you the minimum number of time stamp needed to schedule the operations, provided there is no resource bound, right. So, that is something I can always identify the latency bound, that you whatever the scenario, you cannot schedule this behavior without less than 4 cycle, that is something my ASAP gives, okay. And it also assign the time stamp, this is the earliest possible way, right. So, because it is as soon as possible, so it actually give you the earliest possible time phase where this operation can schedule, and the ILP is the other, right. So, ILP what we give? We give the graph and we give a lambda, that you schedule these operations using this some lambda value, and there is not necessary that it should be 4, because 4 is given, it can give you 5 or 6 anything, and this whatever the lambda you are giving, say this is my lambda minimum, this lambda must be greater than or equal to lambda minimum, right, whatever I obtain from ASAP. So, what this ILP does, it try to schedule the operation as late as possible given the time bound, right, and if the time bound is actually greater than the minimum, I always have a solution. So, ILP gives the last possible or the latest possible way to schedule the operation, and we have already discussed the time terminology. Mobility is the time difference between ASAP and ILP, okay. So, that ASAP and ILP, the difference, for example, this operation is scheduled here in time stamp 2 and this operation is scheduled in time stamp 4. So, that means it can either schedule in time stamp 4 or 3 or 4, right. So, that means the mobility of this operation is actually 2, which is basically from ASAP to S3 ILP, right. But this operation 1 is scheduled here in time stamp 1, it is also scheduled in time stamp 1. So, that means this mobility is actually 0, it has to be scheduled in time stamp 1 if my lambda equal to 4, right. This is the solution where I am given lambda equal to 4, right. So, there is no mobility. So, for this variable I do not need this say suppose this is 1. So, I do not so x1 1, x1 2, x1 3 and x1 4, these are the boolean variable possible the way I have model. I do not need this, right, because they are already, it cannot schedule there, right, it only schedule here. But for this variable 11, so the possible variable is basically x1 11, x2 11, x3 11 and x4 11, that means this operation 11 can schedule in time stamp 1 or 2 or 3 or 4. Here I can see that for this operation cannot schedule in time stamp 1. So, this is not a valid variable, but this 3 is possible, right. So, I am going to take this. So, the conclusion of this discussion is that although there are n into lambda plus 1 number of variable is possible in the worst case, but in general if we just identify the ASAP and ILP timing, I can identify the minimum set of such unknown variables, which is basically the range for each operation. I will identify the ASAP value and the ILP value, and the range from ASAP to L is the variables where this can get scheduled, and rest of the unknown variable I am going to remove. Okay. So, this is something understood, that I have a set of unknown variables and which will be determined by the ASAP and ALAP time, and then let us try to understand. So, this is something the variables. Okay. Now, in the ILP modeling, so next phase is the constraint. What kind of constraint we can have here, right? So, I am going to discuss this constraint without discussing what is my what scheduling problem I am going to solve. That will discuss in the next class. Here I try to say how will what are the possible constraints I will have to model in ILP formulation, and how to model them, because here my unknown variable is xil, right, and I have to model everything in terms of xil, right. So, let us try to understand. So, as I already explained in this, say for example, in this example that so this operation 11 can schedule either in time step 2, 3 or 4, but it cannot schedule multiple times, right. It will always start only one time, right. So, for example, if this starts at time step 2, this must be 0 and this must be 0 if this is 1. If it is executed in time stamp 3, this is 1 and this is 0, this is 0, right, and if it is scheduled in time stamp 4, so this is 1, this is 1, this is 0 and this is 0. So, it means that only one of the xil will be 1 for each variable, right. So, that means every operation has a unique start time, right. So, that means although this I have taken a few variables for each operations, but only one of them will be 1, and that is given by this, right, because so this xil is the variable. So, for each I which is starting from 0 to n, because 0 is the source node and this n is or you can assume that there is n plus 1 which is the sink node, which is always scheduled at lambda plus 1. So, so for each variables I, the summation of this variable, right. So, for this x I y, so I 1 plus x I 2 plus x I 3 plus x I lambda should be equal to 1. So, that means only one of the value can be 1, and here as I already discussed that I will not take for every variable, for every operations this x 1 to x lambda may not be there. It will be determined by this TS and TIL, right. So, this TIS is the schedule time of the operation I in by ASAP, and TIL is the time for the operation I, the ALAP time for operation VI. Okay. So, this particular constant says that although there are multiple variables for each operations, but only one of them is 1, right. So, which is basically say unique start time, right. So, if you take this example, say for example, if you take this variable this ASAP and ALAP and where my time is 4. So, I have already discussed that these operations have only one variable. So, I already know that this operation we are going to schedule in time stamp 1. So, this is x11, x11 is basically x11 equal to 1, so, and this is basically for the source node, right. So, source node is always scheduled in x00, which we can ignore actually, because when this is source node I always know it will be scheduled in time stamp 0. So, similarly, this times operation 2 is only the possibility is 1 time step, because is the ASAP and ALAP time stamp is same. So, this is also x21 is also 1, this is operation 2 time stamp 1. Operation 3, so these are the critical paths. So, this operation has no options. So, these operations will be have a unique value. So, basically I know the start time of this operation, this is already identified for this value if this the lambda equal to 4, but for different value they may not be, I can explain with that. So, this 3 2 and 4 3 is 1, and this 1 2 3 4 5, these are the critical operations. Now, consider this 6 scheduled here and it is scheduled here. So, either it will be scheduled in time stamp 1 or time stamp 2, which is given by this, right. So, either 6 1 is true or 6 2 is true. It means that operation 6 can either schedule in time stamp 1 or operation 6 can schedule in time stamp 2, but it cannot schedule, it can only schedule one of the time stamp, that is why this plus this equal to 1. So, now let us take this operation 9. So, I will just type it. So, this is scheduled in 2, it is in 4. So, it can schedule in 2, 3 or 4. So, 9.2, 9.3 and 9.4 summation will be 1, that means it can schedule one of the timestamp and this must be unique. Okay. So, this is well understood. So, now let us understand. So, suppose it is scheduled in timestamp L or say it is time Ti, because Ti is the start time of the operation Vi, that we have already understood. So, how can I represent this Ti now, because I cannot introduce another variable Ti, I have to represent everything in terms of xil, because that is the unknown variable for us. Okay. So, as I mentioned, this this one of the value is 1, right. So, for example, say x, I am just let me take this 9.1, right. So, 9.2 plus x 9.3 plus x 9.4 equal to 1, right. So, that means we have already know that this can schedule in this timestamp. So, let us say this schedule in timestamp 3. Okay. So, let us say this is schedule in timestamp 3. So, this is actually 1, right. So, and this is 0, this is 0. So, what about if I just multiply this with 2, that means if operation schedule in timestamp 2, operation 9 times x schedule in timestamp 2, I just multiply with this 2. So, this expression I am just multiplying with 3, this I am multiplying with 4, okay, because this is timestamp 4, this variable deals with timestamp 4. So, then what will happen is if I just multiply this with this, it will give me the 3, and where it is scheduled in timestamp 3, right. So, that means if I multiply this xil with L and take the summation, that will give me the timestamp where it is scheduled, right. So, as I explained here is that start time is given by this expression, that is one of, this is a Boolean variable, one of them is true, and if it is true is for in say timestamp L, if I multiply that with L, it will give me the L, which is the timestamp, right. So, then if I just take a summation, because the other that other is 0, so only one of the term will be 1 and that will give me the timestamp. Okay. So, this is very interesting that I can represent this Ti as again summation of Li into xl, right. So, here this is like this, here it is 1 into x I1, 2 into x I2 into lambda into x I lambda, it should be. So, this is what is my Ti, right. So, based on the timestamp where it is scheduled, I can get that L as the timestamp. Okay. So far we understand that I have a Boolean variable xil for each operations. We have understood the limit where this operation can get scheduled, and then we identify the first constraint that the start time of each operation is unique and which is given by this constraint. Okay. And also we have identify how to represent the start time of a variable Vi Ti in terms of xil. Okay. So, let us move on. So, what is the next constraint? The next constraint is obvious, the precedence constraints or the data dependency constraint. So, suppose you have a node Vj and there is a node called Vi, right, and say there is a dependency among them. So, obviously, so say if this is the timestamp is Tj and this is Ti, right, and this node has a delay of Dj. Okay. So, so what does it mean? So, suppose I have scheduled these operations at timestamp Tj, this is my timestamp Tj, right, and this is say this Dj equal to 3. When I can start this operation? When this operation is finished, I cannot start this operation Vi here, because then this data is not available, right. I cannot start my operation Vi here, because then this operation is not done. So, this data whatever the output of these things are not available. So, I can only start my Vi from here, this is Vj. I can start from here, there is no problem, I can start from here, I can start from here, everything is possible, but I cannot start in this timestamp, I cannot start here, I can start here, right. So, that means my Ti must be greater than equal to Tj plus Dj minus 1, sorry plus Dj, because so this should be the greater than equal to this, okay, because this is, if I assume that this is my Tj. So, here this is the Dj, it will take Dj time number of timestamp and I can only start after that. So, this is obvious, And now since I cannot represent, I do not have Tj variable in my ILP formulation, I have only XIL. So, I can represent this as a in terms of XIL, and which I have already discussed that it is basically L into XIL, right. And this is what this Tj is basically summation of L, which is L into XJL, and that's, and Dj is Dj because it is a constant value. So, I represent this in terms of this, and here this L varies from is the possible value of lambda, and this I and j is for all such edges, right. So, for each such edges I will get a constant like this, okay, and this is called precedence relationship or data dependency constant. Okay. So, if I take this example again, and let us say I try to model this say 7 and 6, right. So, let us say I take this edge, okay, and this is here my dj equal to 1 because these operations are single cycle, but it can be multiple cycle also. So, what are the possible value of this 6, because it has mobility 2, even it can schedule in timestamp 1 or 2, and 7 can schedule either 2 or 3, right. So, you can say that you can see here that x72 and 73. If I multiply with 2, so this is my possible start time, right, L for 7, and for 6 it is 6.1 or 6.2, right. So, this is 1 into x61, 2 into x62. So, this is the possible value of extra. You can understand if I just put a bracket here, it will be plus, right. So, this is where this basically T7, right. So, this is the start time of the operation 7, T7, this is T6, and it should be, and since the operation delay of the operation 6 is 1. So, this is my D7, right. So, this must be greater than equal to 0, right. So, this is how I can actually take any edge and I can model that way. So, I have to just identify what is the possible value start time value L, what is the start time value of this, and their difference must be the delay of this node, right. And how many such constant will be there? The number of edges. So, there will be E number of such constant. Okay. I am not explaining the others, you can actually go through and you can understand, but this is something for each such edges. Okay. So, now let us move to the another type of constraints, which is called resource constant. Okay. So, what is the resource constant? The resource constant is something you have given some resource bound. Okay. So, you can first of all assume that you can have say plus, you can have division, you can have multiplication, many type of operations. You in the hardware the multiplier may not able to do addition operation or division operations. So, you have say k type of operator, okay, in say in the behavior, say k type of operator, and for type k the resource bound is ak, right. So, that means if there are say k such operators, so I have the bound is a1, a2 to ak, right. So, this is the for operation type 1, this is for operation type 2, and this is operation type k, and given a vi, note say vi, the type of the operations are determined by the function tau, right. So, I just if I apply tau, this will say this is a plus operations or type operation type 1, operation type 2, operation type 3 and so on. Okay. So, let us say this is what will give me the type of operation, because this type of operations all not same, they are have different types, it can be plus, minus, multiplications and so on. Okay. So, this resource bound suppose I have given. So, what is the resource constant? It should say that every type of resource, the number of operation running of that type must be less than of the resource bound, right. I am repeating again. So, for each type of resource, because there are k type of resource. So, for each type of resource say k, the number of running operation in the timestamp should be of type k should be less than equal to the ak, right. So, that means every time the running operations, the operation that are going to use that this operator type k should be less than of the resource bound, right. So, let me try to understand this equation. Okay. So, this is the basic in plain English, that is the constant, but the first point we have to understand, how do I understand what are the running operation in a timestamp, right. So, you so far this xil gives me the start time of the operation I, but it does not talk about when it is running. So, for example, if my xil is 1, right. So, that means it is timestamp L, and it is a d say there are say 3 cycle operations. So, that means it is running in timestamp 1, it is running in timestamp L, it is running in timestamp L plus 1, and it is running in time L plus 2, right. So, that is, so all the operations start his execution at timestamp L, it is running in all 3 cycles, and every cycle it needs, say this is a multiplier. So, one multiplier will be occupied to execute this operation I, right, or operation Vi, because Vi is running in timestamp L, it running in timestamp L plus 1, it running in operation timestamp L plus 2, and this in every timestamp it is going to occupy a multiplier. So, if the type of this operation is a multiplier, say. So, that means the start time is one thing, that it is where it start execution, but identifying the operation that are running in a timestamp, I have to consider the delay of that operation. Okay. So, how to calculate that operation, let us try to understand. Okay. So, suppose a operation V9, it is starting its execution in timestamp 6. So, that means it is running in this timestamp, right. So, if x96 is equal to 1, that means this operation 9 is starting its execution in timestamp 6. So, it is actually basically it is running in that timestamp. If it started in the timestamp 5, then also it is running in timestamp 2. I am assuming this is a 3 cycle operation. So, if x95 equal to 1, so that means start its execution here, still it is running here, and if say it is x94 equal to 1, that means it start its execution from timestamp 4, still in timestamp it is running, timestamp 6 it is running. So, that means even if the operation start at say this 6 minus 3 plus 1. So, this is my L, this is my di, and this is 1. So, that means if my current timestamp is say L, even if the operation start from x minus di plus 1 in that timestamp, still this operation is going to be considered is running in this particular timestamp L, because that is my timestamp where I am actually currently trying to identify the number of resource needed. In this timestamp also this particular operator is going to occupy a resource. Okay. So, if you just generalize this, so it is basically you can understand that if the operation is starting in Lth timestamp, L minus 1 timestamp, L minus 2 timestamp, or L minus di plus 1 timestamp, right. This is what I have given here, L minus di plus 1 timestamp, it is still occupying a resource in timestamp L. Okay. So, if I try to identify the resource requirement for timestamp L, even if this operation starting if it starting is x I L di plus 1 timestamp, still is occupying a resource, one resource at timestamp L. Okay. So, this is how I can identify what are the operations running in timestamp L, right. So, now you can understand this expression. So, this says that all operations of type k, because I have to take each type. So, where k can vary from all type of resource, say for each type of k, so let us say this is a multiplier, all the operations that are multiplied, so all the operations which are of type multiplier I am going to consider, and from all such multiplication I have to understand what are the operations that are actually running in timestamp L, and that I can give how, it is m equal to L minus di plus 1 to L. I have already explained that even if it start at L minus di plus 1 timestamp, still it is running in L, or it is L minus di or L minus di minus 1 and so on, right. So, all this timestamp it is running, still it is running in here. So, that particular concept is modeled by this expression. So, that means for each operations of type k, I will identify how many of them are actually running in timestamp L, their type, the total number of such running operation must be less than of the resource bound of type k, and this is for each type of resource and each timestamp. So, that means for each type of resource, for each timestamp I am going to get a such constraint. So, if there are say k type of resource and there are lambda plus 1 number of timestamps, so these many number of such constraint I am going to get. Okay. I hope you understand this. So, let me just take an example. So, again let us say take this example and say I have say 2 type of resource, one is the multiplier and one is the ALU, and this ALU can say can do plus, minus and division. right. So, AL is a general purpose hardware unit and there is a multiplier, okay. And say there are two multiplier available and assume here the operations are actually single cycle. So, so what are the operation can live in timestamp 1? So, basically as I tell for each type of multiplier for each type of resource each timestamp. So, I will have 4 constraint because this is 4 timestamp operations 4 into 1 because for type multiplier. So, I will have 4 constant for multiplier, I have 4 constant for ALU. So, I will have 8 such constants. Okay. Some of the constant may not be feasible, for example, here we will discuss that. So, for example, let us now take the multiplier, right. So, in the timestamp, so how many multiplier is possible this 1, 2, 3, 4 because they can execute in timestamp 1. So, this given by x 1 1, this is given by x 2 1, this is by x 6 1 and this 8 1, that means this operation 6 can execute in timestamp 1. So, although there are 4 possibles, since there are resource bound is 2, so only 2 of them can be run in timestamp 1, that is given by this constant. So, that means ASAP will schedule all this for in timestamp 1, but because if you have a resource bound is 2, only 2 of them can execute in timestamp 1, right. Similarly, in timestamp 2 this operation can schedule, this can schedule, this also can schedule, right. So, this can schedule here and this can schedule here. So, this can schedule here and this can schedule here, right. So, that means 3, 6, 7 and 8. So, this x 32, x 62, that means operation 3 in timestamp 2, operation 6 in timestamp 2, operation 7 in timestamp 2 or operation 8 in timestamp 2. So, total number of such operation must be less than equal to 2 and so on, right. So, similarly, for the ALU operation I can identify, I am not going into detail of those each expressions, but we can understand for each type of resource, each timestamp I will have a constraint which makes sure that the number of runnings operations in that particular timestamp will be less than of the resource bound. Okay. So, this is what the resource constant. You can also have a latency bound that you have given that this latency lambda plus 1. So, latency actually I have already explained that lambda will be used to execute this part, this will be 0 and this is lambda plus 1, right. So, this 1 to lambda will be used to execute the actual behavior, right. So, what I have to do? I have to make sure that, so what, how do I decide the timestamp of this? This is n operation. So, x n l, this is the execution start time of this operation n, and if I multiply this with L and if I just do a summation over L, this must be less than or equal to lambda plus 1, right. So, that means I am going to schedule everything and make sure that the Sonk node must schedule in timestamp L plus 1. So, then if this is scheduled in lambda plus 1, that means that it indicates that all the operations in the behavior actually schedule within 1 plus lambda. So, it ensures that my latency bound is met, right. So, this is how I can actually explain the latency bound. Okay. I hope you understand this. So far, I have understand that I have these variables x I L which determine the start time of each operations, and I have 4 type of constant I have discussed. One is the this start time must be unique, next is precedence constant or the dependency constant, the resource bound and latency bound. And now, what could be the objective function? What is the objective functions? So, objective function, as I mentioned, it is basically given by this C t into t. T is the start time of the operations. Okay. So, this t is nothing but this expression, right, x l into x I l. And if you now try to optimize this latency, okay, if you try to optimize the latency or try to reduce this timestamp, what is the value? I want to schedule this this node as soon as possible, right, so as early as possible. So, that means I can give this my this T n will become this this value, and then this constant, this C should be 0 0 0 1, because I want to. So, that means what? This is basically 0 into. So, you can understand this T, this is a multiplication of this 2, right. So, basically it is basically C 1 into T 1 plus C 2 into T 2 C n into T n, and this T I is nothing but this expression, right. T is the start time of operation I, and if I want to minimize the latency. So, that is, if this is my objective function, how I can get the this value minimum? If I put this equal to 0, C 1 equal to 0, C 2 equal to 0, C3 equal to 0 and this equal to 1, because otherwise this value will be more, right. So, if I just put C1 equal to 0, C2 equal to 0, everything is 0 except the Cn, which is the basically the sink node constant. So, then my this optimization function remove to Cn into Tn, because other values become 0, and then only I can get this expression value minimum, right, because I want to minimize the latency. So, to minimize the latency I will take those constant whatever I have just discussed, but I will make my latency constant C is this 0001, and I will just multiply this with this Ti, which is the start time of this, which can be represented by this in terms of Excel like this, and then I will get this latency value. So, what I am trying to say is that I have those constant and just try to minimize the latency, I just take this constant, and if I just run the ILP solver I can get the minimum latency. Similarly, say I want to do ASAP using ILP formulation. So, ASAP means what? I want to start this operation as early as possible, right. So, then what I have to do? I have to, so if this is my expression, when this value will be minimum, if this value, if these constants are basically 1, right, because here thus I want to get the minimum value of each start time. So, what I am going to do? I am going to put C1 equal to 1, C2 equal to 1 and so on. So, then this operation become T1 plus T2 plus Tn should be minimum. So, I want to get this value is minimum. So, when this value, this what is T1? T1 is nothing but say 6 1 and 6 2, 2 into 6 2, because T1 is given by this. What is say T2? It says T2 is say 7. So, the 7 is given by this, right. For 8 is given by this is the possible start time. And what is the 9? So, for 9 it is 9 to this, right. So, this is the possible start time of this operation 9. So, when this operation will be minimum? If it can schedule here, right, if it is scheduled here it will be 2, if it is scheduled here it will be 1. So, if I just take the summation of this value, obviously the ILP try to schedule this into timestamp 1, because if it is try to schedule in timestamp 2 it will this value will become 2, if it is scheduled in timestamp 1 it will be 1. Similarly, for this it will try to schedule in timestamp 2, not in 3, because if it is try to schedule in timestamp 3 it will be 3, otherwise it will be 2, right. So, you can understand that just having the same constraint and say I want to get a ASAP solution with resource the timing constant, I can just set the value of this C1 all 1 and I can run the same ILP, it will give me a ASAP solution. Okay. With this I conclude today's class. So, in today's class what I have discussed, how we can model this scheduling problem into ILP, what are the possible constant and how to identify the constant and what are the number of constant is there. So, that we have discussed. In next class what I am going to do is I am going to say how I can model this MLRC problem as a ILP, right, using this constant, or how can I model this MLRC problem, minimum latency under resource constant, as a ILP problem using this constant, right. So, that I am going to discuss in the next class in detail. Okay, thank you.